Hi everyone, I'm Abby. I'm a PhD student at University College London, and I'm working on the LEGEND experiment. So today I'll be talking about the active volume characterization of the germanium detectors for LEGEND-200. And this work is really a joint collaborative work between myself and Valentina, who's also here. So shout out to Valentina. Okay, so a brief introduction about LEGEND, because I think actually no one knows what it is. So it's a new Mutualistic double beta decay experiment, and it's an acronym that actually makes sense in my opinion. So it stands for the Large Enriched Germanium Experiment for Mutualistic double beta decay, and the mission statement is to develop this two-phased germanium 76 based Mutualistic double beta decay program that will eventually target a half-life sensitivity of 10 to the 28 years. So this is really huge. The collaboration has currently got 260 members across roughly 50 institutes worldwide. So really brief introduction about Mutualistic double beta decay. I don't have to talk too much about this because now we've covered this in lectures, but yeah, it's this hypothetical decay, and detecting it would be really monumental because, well, it would prove that neutrinos are Majorana in nature, i.e. they're an antiparticle. It's also a lepton number violating process. So this could offer some possible insight into the matter-antimatter asymmetry problem of the universe. And also the whole process is sensitive to the absolute neutrino mass scale and then the neutrino mass ordering. So there's lots to be gained from this if it was ever to be detected. You can search for this in various isotopes, and actually we have lots of different experiments using these different isotopes and different methods, but they have to be even. And I've underlined germanium 76 because that is what LEGEND is using. And the experimental signature for this is just this monoenergetic peak at the end of the 2nu spectrum. And the Q value for germanium 76 is around 2 MeV. So LEGEND is using this two-phased approach. So I'll quickly introduce these phases. The first phase is LEGEND-200. And this is currently in the commissioning phase right now. So it's a very exciting time. It will use 200 kilograms of enriched germanium to probe this decay. And this corresponds to a half-life sensitivity of 10 to the 27 years. And you can convert this half-life sensitivity into an effective Majorana mass using this equation here. So you can see they're sort of inversely proportional. And this would correspond to a mass sensitivity of 30 to 70 MeV. And the range is because, as we previously said, we've got these large uncertainties on the nuclear matrix elements. The next phase, LEGEND-1000, which is our future sort of R&D phase, will use 1,000 kilograms of enriched germanium. So this obviously boosts the half-life sensitivity by an order of 10, a factor of 10. And then this, again, probes an even higher, a lower neutrino mass sensitivity. And the exciting thing about LEGEND-1000 is actually it fully covers the inverted order region of the parameter space. So if, depending on the result of that, we can learn something actually really important. And I put like a number 1 there because recently LEGEND-1000 was sort of selected as the best future experiment for neutrinistic double beta decay by the DOE, and they've sort of agreed to fund it. So it's now kind of hopefully going to become a reality. But anyway, I'm focusing on LEGEND-200. But yeah. So really brief experimental details on LEGEND-200. So LEGEND-200 is really the daughter experiment of 2 previous germanium 76 based neutrinistic double beta decay experiments. The Gerda experiment, which was already talked about earlier today, and actually the next talk by Valentina will focus on this, and also the Majorana demonstrator experiment. So it's actually located in the exact same location as Gerda using the same cryostat. So that's at the Gran Sasso National Laboratory in Italy. And LEGEND uses these germanium detectors that double up as both the source isotope and the detector. So this is kind of like the unique selling point of LEGEND. And it also uses liquid argon scintillation light detector vetoes that surround the germanium detectors. And then this is also surrounded by water. So there's lots of layers to sort of really reject our backgrounds, because background control is the most important thing in experiments like this, where the signal rate is expected to be so low. And yeah, the plan is to take 5 years of data for a 1-ton exposure starting essentially now. So we are really in the commissioning phase. We're taking our first data now, and then hopefully the first physics data is expected later this year. Oh yeah, and a quick note on the background index. So the target index for LEGEND-200 is 2 × 10⁻⁴ counts in this sort of energy range exposure. So yeah, I just got some brief photos from the commissioning. So, because I just think these are really pretty photos. So you can see here, we have these strings of germanium detectors that are connected like this. And the plan is to eventually deposit them in this circular array And they are surrounded by, in the inner and the outer parts, by these wavelength shifting fibers. So these form part of the liquid argon active veto. So they gather any scintillation light and then transport it to the silicon photomultipliers. And then this will be deposited down into the liquid argon cryostat. So yeah, that's going on now. So yeah, the focus of my talk is more on germanium detectors. So brief overview of that. So we use these high purity germanium detectors, which are semiconductor devices, which are capable of measuring the energy of charged particles in gamma rays. And obviously for mutualistic decay, we're looking for this monoenergetic peak at a certain energy. Obviously for LEGEND, we care about germanium 76. So these detectors are enriched in this material. And these detectors have really, really high energy resolution, roughly like 0.1% at the Q value that we're looking for. So they're really good, basically. And this all increases our sensitivity. And we have different geometries of these germanium detectors. I won't talk too much about this, but the sort of state-of-the-art new type of geometry we work with is this so-called inverted coaxial point contact detectors, or ICPCs. And basically, they have a really unique design that allows them to have a really large detector mass while still having good energy resolution and good signal against background discrimination. So this is why they're so good. Yeah, so onto the active volume. So the sort of something that needs to be done before we actually get our final results and take data and stuff is to determine the active volume of every single germanium detector in the experiment. So this is because these germanium detectors have a dead layer around the outside, where if energy is deposited in this region, it won't be recorded at all. So we need to try and figure out the active volume by knowing this dead layer. So this is the conductive layer on the surface. Now the actual picture is a little bit more complicated, and we also suspect that there is this transition layer where you have partial charge collection. So if you look at this diagram here, you can see how you could model this profile as a function of the distance into the detector. So you have, like a dead region, a sort of partial transition layer region, and then we define something called the full charge collection depth, which is the sum of both the transition layer and the dead layer. But actually, we can kind of ignore the transition layer at this first stage. Now, the reason we care about this dead layer and active volume is because, well, actually, the neutrino beta decay half-life sensitivity is a function of the active mass. So we really do need to know this to then actually compute these sensitivities of the whole experiment. And also, we could possibly get these degraded events where some of the energy of events is deposited in the dead layer and the sum is in the active volume, and then it changes the energy so that perhaps it could end up in our region of interest and like mimic the detector signal. So we've got to be careful of that. And to actually determine the active volume, we do this empirically by comparing the characterization data of these detectors with simulations. So the characterization takes place in different underground labs, actually not at LNGS, but in dedicated characterization labs. So one of the main ones we use in LEGEND is the Hardy's underground lab in Belgium. So under there, each individual detector is exposed to a range of different radioactive sources, and the data is taken. And this is done extensively before they're then deployed at LNGS for the final run. So yeah, this is just a sort of photo and diagram of what's going on. And this is ongoing work. So yeah, how do we actually use this data then to determine the active volume? Well, yeah, as I said, we're comparing simulations of data. Specifically, these are Monte Carlo simulations of the source isotope and the detector in its test stand. And then what we do is we apply this dead layer post-processing. So to sort of artificially simulate different dead layer thicknesses, we do this position-based weighting and removal of energy deposits based on their position within the detector. And then we do this lots of times to simulate different values of the FCCD or the dead layer. And then we compare this with the data. And then in the analysis step, to make the actual comparison, we compute some sort of observable, which in this case is this gamma line count ratio. And I'll get onto that in the next slide. So yeah, so we can do this with two different radioactive sources, but in general, they have to be low energy. So I'll be talking about barium-133, but we can also do it with americium. So the count observable, or the FCCD sensitive observable for this is this count ratio here. So it's the number of counts in certain gamma peaks. So in this case, it's the 79 and 81 keV gamma peak divided by the 356 keV gamma peak. And then this is computed for every post-process simulation and the data. And then it's really simple. You can just see the intersection and infer the best fit FCCD. So for example, for this detector, it's around 0.9 millimeters. And then this is repeated for every single detector that we eventually use in Legend. So to double check that what we're doing makes sense, we can then actually compare this whole spectrum of our data with the best fit Monte Carlo simulation. And here's an example one for one of the detectors. And as you can see, in general, the fit is quite good, but you do get some deviations at certain energy ranges. But this isn't a problem because this is expected because at this stage, we haven't modeled the transition layer. And the transition layer is what causes the sort of push out of the full energy peak into the lower peak regions. And that's why you get a discrepancy there and then at the lower energy as well. So yeah, that's the sort of incomplete part of this model, but this doesn't affect the estimate of the FCCB. So yeah, this is repeated for lots of detectors. So far, we've done 30 ICPCs at Hardy's, and these are the results. So here we've got the barium results. And as I said, we can also do this for other radioactive sources. So americium-241 is also shown here. And you can see there is a systematic offset between the two. And this is actually kind of a long-standing problem that we've had in Gerda and Legend, where they follow each other. But for some reason, we have some sort of energy dependence that still needs further investigation. But the good news is that we have some estimates of the FCCD for all of them. And currently the plan is to just take a sort of combination of a weighted average of the both to get the final active volumes. Yeah, and then a sort of last talking about the transition layer. So I mentioned how there was discrepancies between them, and this is the transition layer part. So the sort of work we're doing now is to start modeling this transition layer. But it's really not a trivial problem because we don't really know what the transition layer should look like or what it should be. Here I'm showing a model for a linear transition layer, but really like we don't have any intuition as to what the profile should be. And like you could model any function or any number of parameters. But yeah, here you can see already using a linear transition layer with certain slopes is already improving the match between data and simulation. But yeah, this is work in process. Yeah, so to summarize, Legend is searching for neutrino beta decay in Germanium-76 in 2 phases. The first phase, LEGEND-200, is now commissioning and it's slowly ramping up to 200 kilograms of germanium detectors. But before these detectors can actually be used, they're characterized. And this is also ongoing work at the Hardy's lab. And we've sort of so far successfully computed this active volume using the dead layer. But the next step is to also model the transition layer, which will be useful for other analyses and things as well. Yeah, that's another photo of 2 strings in the lock in the clean room of Legend. Yeah, thanks for listening. Any questions?
Abigail?
So I put some random photos.
Is this you or?
That is me, looking really
okay,
stupid.
or twice actually. Okay.
Yeah.
Questions? Let's start.
Thank you for the talk. Will Legend-200 have other physics searches going on?
Yeah, so obviously the primary physics searches the neutrino beta decay, but there's also the 2 new double beta decay analyses that can be done. And then this is also related to BSM searches at lower energy. I actually don't know too much about this. I think Valentina's been working more on this, but basically in the lower energy ranges, you could have new physics. And this has been done for Gerda, for example, so it will definitely also be done for Legends.
And do you know how long you're going to be running for?
5 years. Hopefully by the end of this year, we'll be in full physics data taking mode. So currently we're just commissioning and building up to the full array. But so say if we start at the end of this year, 5 years uninterrupted, that would be pretty good.
Thank you.
Joachim was next.
So you mentioned that one of the motivations for characterizing exactly the active volume is that degraded events could mimic the neutrino beta decay signature. Is there any way you can guard against that? Is there some way of determining event by event whether the event happened deep inside the bulk or close to the surface?
There's this drift time parameter that you can compute from the waveforms of the germanium detectors. So I guess you could apply a drift time cut. We also have this analysis called A/V, which is the signal to background discrimination we use, where you can discriminate single site events against multi-site events. So probably this event you're describing here, where some of it's in the, actually no, because we would miss the multi-site part of that. I think maybe it would still look different in the the waveform would still
from
look
the
different.
pulse shape then.
Yeah, I think the pulse would still look different, but I actually don't know, but that's a good question.
Can I ask a second question? Regarding secondary physics goals at 1 ton year, at what point do you start seeing actual neutrino interactions? I mean, solar, atmospheric, whatever. Because for dark matter experiments with a similar exposure, that is slowly becoming an issue, right? I mean, not an issue, but a feature.
Is it, sorry, I'm asking Valentina here. Is it one of our known backgrounds, the neutrinos from, I didn't know that. It should be.
I don't think it would affect your background so much because you know exactly where you're looking for neutrinos, double BTK, but it could be one of your signals. It could be an additional signal that you can look for in a different energy range.
I don't actually know, but yeah. In theory, yes.
There was one last question. There was one question. Last question is coming from the back.
Okay, I'm far from experimental physics, so my question is, now you are characterizing these detectors, and then you're characterizing this active volume, and the experiment will be running for 5 years. Would you expect, for instance, some degradation in the active volume, and how do you assess this issue?
Yeah, this is a really good question, actually, because we don't, there's this thing called dead layer growth that has been a massive problem for Gerda, actually. So there's this theory that, well, it's actually an observed effect that the dead layer increases its width over time, but only when the detectors are warm. So in theory, while the detectors are cold, we expect the FCCD to remain consistent throughout the data taking. We had some problems with Gerda because between the phases, the detectors were removed from the cryostat and left in a warm environment, and then potentially that FCCD grew and then put back down again. So then at the end of Gerda, we had to remeasure the FCCD of this, and then sort of basically it wasn't an easy problem to resolve. So this is a good question, but I think while they're actually in the experiment in the liquid argon, there should be no reason why the active volume should change.
So would you make another measure after the end of the experiment?
At the end of LEGEND?
Change? No.
No.
Another characterization, I mean, to compare if there were
I don't know
changes.
what they would do, but I mean, I personally would say it's better to always take more, but then there's all of the cost that comes with that campaign. I think they would, I feel like they would be recharacterized before LEGEND-100, right?
Maybe yes, only because LEGEND-100 will be not in Gran Sasso laboratory, as well as the LEGEND-200, but in Snow Lab. So maybe to do this movement of the detectors, maybe it's better to do another characterization. But as Abigail just said, that we don't have any reason to think that the FCCD would be changed if they stay at the same condition.
Thank you very much. Thank you, Abigail.